Okay, this problem is again from aldehyde and ketone. You see, you have an aldehyde this side, you have CH2, CH2, CH2OH, this side you have an alcohol group. If this compound is treated with CH3OH in the presence of HCl, the product formed is this. Then you have to write down the mechanism for this reaction. So sufficient hint will be given. Like you see, this OCH3 had attached to this carbon. This means, and this carbon is also attached to one oxygen. This means this carbon that is attached with oxygen, there must be this oxygen attached to this carbon. So there must be one attack of oxygen on carbon. One thing I know. Now also, you see, this oxygen also attached to the carbon. So this means there is one oxygen that is attached to two carbon. This is possible only if either this oxygen attacks on this carbon. In that case, this carbon is attached to this oxygen and this oxygen is also attached to this carbon. So this means this suggests something about attack of this oxygen to this carbon. Now there is sufficient hint, and you have to also attack this oxygen on this carbon. There are sufficient hints. Using these hints, you write down the mechanism for this reaction. You have to remember something about hemiacetal formation and acetal formation. Medium is given acidic. Let us wait for 30 seconds. Let us discuss the solution. Okay, so you see, I can always write, so this product, this reactant can be written something like this. You have a CHO, CH2, so CHO, CH2, CH2, O, CH2 and OH. 1, 2, 3 CH2, 1, 2, 3 CH2 and OH, and then you have CHO group. In the first step, I have protonated this oxygen, so we have OH plus. Now in the solution we have two nucleophiles that can attack. Either this oxygen can attack because it has lone pair, or this oxygen can attack. If this oxygen attacks, then it is intramolecular reaction, this intermolecular. So in the first step, let us do intramolecular. Intramolecular reactions are always faster than intermolecular. So the first step is nothing but intramolecular, because intramolecular is always faster than intermolecular reaction. So first step is intramolecular. Now this attacks here, this opens up, so you will have 1, 2, 3, 4, 5 membered ring. So you have a 5-membered ring. So this is a 5-membered ring. So let me write. So this is a 5-membered ring. Now this contains OH plus. So in the next step I can lose H plus. So if this goes here, so I can mix oxygen lone pair. So if I release H plus, that is a minus H plus, I can write, if I release H plus, this oxygen is free from H plus. Now OH group is here and this is here. Now this is nothing but hemiacetal. So this is a, if you remember this compound is called hemiacetal. Did you remember what we have done? This compound aldehyde or ketone with one OH group is called hemiacetal. In the next step, if you remember, H plus will attack here and will make OH2 plus, something like this. And now once OH2 plus is a good leaving group, it will release. And the same point of time, we have one another nucleophile, that is CH3OH. Now oxygen will act as a nucleophile. As soon as this goes, this will attack here. Now if attacks here, you will get this product, CH3O, and oxygen will have a formal charge because it has 3 bond, 2 bond plus 1, 3 bond. Now oxygen is a formal charge, positive charge, so it will lose H plus in the next step. If it is loose H plus, it will form something like this, OCH3. Now this carbon is attached with 2 oxygen. This side you have oxygen. Initially this was ketonic carbon, so this is a ketonic carbon, or you can say carbonylic carbon. So this is your carbonylic carbon initially, that has been attached with 2 oxygen. So carbonylic carbon is basically attached with 2 oxygen. Attached with 2 oxygen. Now if you remember, this compound is called acetal. So this is nothing but, so this compound is a acetal. So you have some idea. If it is connected with 1 oxygen, this is called hemiacetal. If it is connected with the 2s2 OH oxygen, it's called acetal. Nowadays both are called, as I remember in Solomon they said both are acetal, but the previous concept is they are calling hemiacetal and another is called acetal. Now sometimes acetals are used to protect a group, something like this. If we have a ketone, and let us say here you have a double bond. If you want to reduce this double bond only, you don't want to reduce. If you treat with H2, what will happen? This will happen. This OH group will be reduced as well as double bond will be reduced, H2PD. So both will be reduced. You will have OHH and this double bond is gone. So both will be reduced. Now if I want to reduce only double bond, I don't want to reduce the carbonylic carbon, I can make the hemiacetal and then do reduction. So what, and these all steps are basically reversible. So hemiacetal and acetal formations are reversible. So this also is important point. Acetal formation is reversible. All steps are reversible. So acetal formation is reversible. Now what we can do is, first I want this product, double bond reduced, but ketone group does not reduce. This I want to reduce only double bond, but if I do this, I will reduce both. So what can I do? First I will make hemiacetal. So let us treat this compound with OH. Okay, so this compound if I treat, I will get, so in basic acidic medium, I will get something like this. Are you getting or not? And here you will have a double bond. Now if you do reduction H2PD, now I will able to reduce double bond, but there is a compound this not will reduce, this is acetal. Now acetals are reversible. Now treat with H plus. If you treat this compound with H plus, you will back to pavilion, you will have ketone. Are you getting or not? Because these all steps are this step is not reversible. This step is reversible. So you can always you make a acetal and then you hydrolyze the ester. So this is acetal. So you first form the acetal. So first step is formation of acetal, and the last step is, you can say, hydrolysis of acetal. So this is hydrolysis of ester. This step is formation of ester. Ester formation is always reversible. So even this step is reversible. Ester formation is reversible. This you have to remember. So this reaction is related to acetal formation. So you have to remember, acetal is something when you have 2 oxygen attached to the carbonylic carbon. Hemiacetal is something in which you have only 1 oxygen attached to the carbonylic carbon. When we use acetal, if I does not want to do something with carbonylic carbon oxygen bond, and I want to do something in the other part of the molecule, in that point of time, we make acetal and do whatever I want to do with the other part of the molecule, and then we do hydrolysis, and then we will get the same molecule again. Okay, we'll discuss the next problem.